lesson, we're going to build on what we learned about writing formulas for ionic compounds and take it one step further. Up to this point, we've worked with monatomic ions, single atoms that gain or lose electrons to form ions. Sometimes a group of atoms can bond together and act as a single charged unit. These are called polyatomic ions. On this slide, you can see examples like phosphate and ammonium, which is the NH4. Notice something important. Even though these ions contain multiple atoms, they behave as a single particle when forming compounds, which is why we have these little bubbles drawn around them. By the end of this lesson, you should be able to recognize and write formulas containing polyatomic ions and correctly name ionic compounds. So naming ionic compounds, the first rule is, just like with the formula, the cation comes first, and it gets to keep its name. Actually, most of the time, the IUM that's in the cation tells the listener that there is a positive charge. That's why pretty much a lot of the metals have names that end in IUM because they form cations. If the compound contains a transition metal cation, we have to indicate the oxidation number. Remember, they can have a lot of different values. And we're going to use Roman numerals in order to indicate that. So for example, gold with a +3 charge, and it doesn't make any difference whether it's 3 plus or +3, will give you, in the name, it'll be written as gold, parentheses, Roman numeral 3, close parentheses. And then the name of the anion is changed so that it ends in IDE. Now that accomplishes two different things. It tells the listener you're talking about a compound. It's not just chlorine. It'd be chloride, for example. The IDE also tells the listener that it has a negative charge. So that as soon as you hear something like nitride, you can say, oh, that's nitrogen with a -3 charge. So like I said, chlorine, chop off the ending, chop off the INE, goes to chloride. Some of them get a little kind of, it depends on usage. So oxygen, instead of like making it oxygenide, is just oxide. The OX is apparently the important part there. All right, so here we have some examples. We have AuCl3. Now there's a couple of different ways that you can figure out what the oxidation number is on that gold. You can either kind of do a reverse swap and drop if you have a halogen, or a halide, I should say, as part of the compound. And so that would tell you, if you were going to use that method, that this would be gold with a +3 charge. Probably a safer way to do this is to, got to turn my pen on, is an algebraic method. So we say, all right, we want to figure out what the charge is on the gold. So we're going to give that an X. Then we have 3 chlorides. Each one has a charge of -1 because it's in group 17, and it adds up to 0 because it's a neutral compound. Remember when we were using all those crazy pictures, we wanted to make sure we ended up with a nice rectangle afterwards because that told us that it was neutral. So we solve for X, and we get that X is equal to +3. So in that case, we're going to have that AuCl3, the name of it will be gold 3 chloride. Now the next one does not have a transition metal in it, so we can just say it straight out. So the first ion gets to keep its name, sodium. Notice it has an IUM in it. And the second one, we'll chop off the ending of nitrogen and make it nitride. So that's what that one would be. Now here we have lead it actually has 2 different oxidation levels. And so for lead and tin, we have to remember to check what the oxidation number is. So I'm going to erase this. And so I have a little bit more space. I didn't set up this slide very well. So we have PbO2. I'm going to write it like that. So we want to figure out what lead is. So that's our X. We have 2 oxygens. Oxygen's always -2 when it's in a compound. Adds up to 0. So this is lead with a +4 charge. Another way you can do it is you kind of write over it. So 2 times negative 2 is going to be minus 4. So that means lead has to be plus 4 in order for it to be neutral. It all depends on how you want to do it. So we go ahead and we write it down. So it's going to be lead 4 oxide. Remember, with Roman numerals, if you have a 1 before 5, it's a 4. If you have a 1 after 5, it's a 6. So let's use that second technique in order to figure out what PbBr2 would be called. So we have 2 bromines. Each bromide is minus 1, so that means we have a total charge of minus 2 from the bromides. So that means that this has to be lead with a plus 2 charge. So it'll be lead 2 bromide, and it's down at the yellow box. It's just reminding you that if you have lead or tin, that you have to be, so let's write that down here. They can have more than one oxidation number. They can either be plus 2 or plus 4. And the reason why they can be different as compared to the ones that are a little bit higher up in the periodic table is because they're much farther down. They just have a lot more electrons that can start bouncing around at the different energy levels. All right, so now let's try some. So the first one we see is silver. Remember, silver is always going to be plus 1, so we don't have to worry about figuring it out. So that would just be silver fluoride. And then we have MgCl2. Magnesium is not a transition metal, so then that would be magnesium chloride. When you are working with magnesium, don't get it confused with manganese. Let me write that, which is a transition metal. So if you see Mn, that's a manganese. If you see Mg, that's magnesium. 2 totally different elements, very different properties. Okay, so the next compound has iron. Iron is a transition metal, so we have to figure out the oxidation number. So let's see, we got, I need my pen. We have 3 chlorides. Each chloride is minus 1, so that means our negative charge total is minus 3. So this is iron with a plus 3. So that would be iron 3 chloride. Next one up is aluminum with sulfur. Aluminum is not a transition metal, so we don't have to worry about figuring out its oxidation number. It is always plus 3, so it'll just be aluminum sulfide. And then we have TiO2. Titanium is a transition metal, so 2 times the negative 2 from the oxygen is minus 4, which means that this is titanium with a plus 4. It's with these oxygens and anything else that's in group 16 that the reverse swap and drop really doesn't work. So probably doing it this way, where you figure out your total negative charge and then figure out what your positive charge is, works the best. It's safe, much safer, more reliable than using the reverse swap and drop. So this would be titanium 4 oxide. All right, so like I said, we're going to extend out our formula writing with ionic compounds using polyatomic ions. So just like it says, it has many atoms. It also tells you that it's an ion, which means that it carries a charge. So for example, if you take 1 phosphorus and 4 oxygens plus 3 extra electrons, you get the phosphate ion. Its formula is PO4, and it has a minus 3 charge. I have a lot of people say, well, why is it phosphate? Why not, I don't know, something else? And it's just kind of like you have people who have their own names, like Anne, Jeremy, Tim. That's what their name is. And so PO4 with a minus 3 charge, its name is phosphate. Now, when you work with polyatomic ions, you need to pretend that there is a little, like a little force field surrounding them, and it's keeping that polyatomic ion together. So, because when you write formulas, a lot of times when people first start doing this, they're very tempted to take them apart, and they start doing their swap and drop with the numbers that are down below. So we're just going to be working with the charge, so that's the number that's up top. We're not going to take the rest of the polyatomic ion apart. There's a whole bunch of polyatomic ions. Probably the most common ones are shown on here. One that's key is the only positive one that we have, and that's ammonium. So it's NH4 with a +1 charge. It's the only positive polyatomic ion you need to worry about. Notice the name ends in IUM. If it were NH3, it would just be ammonia, not ammonium. So we have a bunch that have a -1 charge overall, which is how this thing's grouped together. So we have acetate and cyanide. Hydroxide is a really important one. It gets used a lot, and for some reason it gives people a lot of trouble, so I'm going to put a circle around it. And then we have nitrate, perchlorate, permanganate. We have some that have a -2 charge, so like carbonate and sulfate. And then phosphate is probably the most common polyatomic ion with a -3 charge. When you were looking at names of you have the name of the compound and you're trying to write the formula, pay attention to whether the name has an 8 in it, because that will get you most of the way there, because most of these end in 8. So as soon as you see that, you get your list of polyatomic ions out. And your reference packet, which you are always allowed to use on the tests, has a very comprehensive list of polyatomic ions. Notice that probably the reason why it gives people trouble, the hydroxide one, doesn't end in 8, even though it is a polyatomic ion. However, it does have, let's switch back to red. It has that hyd part, which tells you it has hydrogen, and it also has ox. So it tells you that it has hydrogen and oxygen in it. You just have to be paying attention. All right, so we're going to go back to the pictures for a little bit, and we'll see how we write formulas for ionic compounds containing polyatomic ions. So aluminum is +3, nitrate, we look back at the list, it's got that ATE on it, is NO3 with a -1 charge. So there's our picture. We have the 3 missing electrons. Each nitrate has 1 extra electron, so it's going to take 3 nitrates to get a neutral compound. And then the formula would be Al parentheses NO3 close parentheses 3. The reason why you need to have those parentheses on there is if you don't have them, it would say that you had 1 aluminum, 1 nitrogen, and 33 oxygens, which is a very ridiculous compound. That would never exist. So in general, if you want to put parentheses around your polyatomic ions all the time, even if you don't need them, I think I would rather have you do that than leave them off when you really do need them. All right, so let's do another example. Ammonium and carbonate. So here we have that ammonium one. So remember that is going to be NH4 with a +1 charge. It's not Am from down near the bottom of the periodic table. That's mercutium. Then carbonate, we have that ATE, so we look it up. CO3, draw the pictures. So there's ammonium. It's missing 1 electron, so it has 1 divot. Carbonate has 2 points because it has 2 extra electrons. So we're going to have 2 ammoniums and 1 carbonate. And so we use the parentheses around the ammonium in order to show that we have 2 of those ammonium compounds, polyatomic ions. And then the last example, aluminum and phosphate. We got aluminum is +3, phosphate's -3. They are already charge balanced, so we know it's just going to be AlPO4. Now, something that a lot of textbooks do, and it makes me just a little crazy, is that they call all compounds molecules. Remember, we have a crystal lattice of these things going back and forth. That's why, or alternating between cations and anions. That's why we are always going to simplify our formulas down to the lowest whole number ratio. Make sure that you are keeping your force field intact. You don't try to do anything strange with the numbers of elements inside the parentheses. And so because it is a unit for that particular formula, if you're talking about an ionic compound, it's called a formula unit, not a molecule. Molecules are only for covalently bonded compounds. All right, so do some practice swap and drop with polyatomic ions. In this case, swap and drop kind of goes to swap and drop the top. Maybe I'll write that up at the top. So we got swap and drop the top numbers. And that that hashtag symbol is called an octothorpe, actually. My generation called it a pound symbol, and it stands for number. I used to assume that my students knew that, and it turns out they didn't. I kind of wonder what they thought I was doing all that time. All right, so we got sodium and phosphate. So sodium's in group 1, so it's +1. Phosphate has that ATE on it, so we look it up. It's PO4 with a -3 charge. So we're going to swap and drop the top numbers. So we're going to end up with 1 phosphate and 3 sodium. That 4 at the bottom goes along for the ride. You don't take it apart. Remember the force. All right, do another one. We got ammonium. That's that positive polyatomic ion. And sulfur. So we have 1 ammonium, and we have a charge of +1 on the ammonium, charge of -2 on the sulfide. So when we do the swap and drop the top, we end up with NH4 twice, and then the S. Then carbonate and silver. Remember, silver is always +1, metals always go first, so you end up with Ag2CO3. Now here's hydroxide. That was the one I said that people have trouble with. It says it has hydrogen and oxygen in it, so we looked that up. It's OH with a -1 charge. Zinc is always +2. So when you do the swap and drop and put the zinc, put the metal first, you end up with Zn parentheses OH twice. So the next one has there's phosphate, has a Roman numeral that tells us what the charge is on the iron. Let's see, can I do an arrow? So that goes with what's in front of it. It doesn't mean that you have 2 irons. So we swap and drop the top numbers, and we end up with Fa3, so from the charge on the phosphate, PO4 in parentheses, and then we have 2 phosphates. And ammonium and carbonate, that one was done on the previous slide, so it really needs to be taken out. And then we have gold with a +3 charge and acetate. Now acetate really bothers people because it has so many letters in it. And so sometimes what I tell people to do is just go ahead and like put a circle around it or put parentheses around it ahead of time so that you don't try to take it apart. So we end up with needing 3 acetate anions. And so it ends up being Au parentheses C2H3O2 close parentheses 3. All right, naming ionic compounds with polyatomic ions. The nice thing about them, writing formulas can be a little tricky sometimes, but they're already special. You don't need to change their names at all. So if you had something like CaSO4, that would be calcium sulfate. The only thing I've ever run into as far as people having trouble with is they tend to want to name all of them in order, and they don't kind of back up and think about it. So if you have a binary compound, that's what we talked about in the previous lesson, you have 2 capital letters. So that's the one where you change the ending of the second element to "ide." If you have a polyatomic containing one, it is going to have more than 2 capital letters. So we look at this and we say, all right, we definitely have more than 2. We have 3 capital letters. So therefore, I need to get my polyatomic list out. And I see that, oh, SO4 is sulfate. So that's why it would be calcium sulfate. Here's another one, has more than 2 capital letters, so we say, all right, it's got a polyatomic ion on it. So we look it up, we find out that, put that over there, NH4, we're reminded that, is ammonium, so this would be ammonium chloride. You still have to change the ending of the second element in the formula if it is not a polyatomic ion. And then this one got lots of capital letters, so there's the first set, so that's the ammonium, and then there's the second set, and that's nitrate, so ammonium nitrate. All right, so we got some guided practice, so I got to get my pen, do some practice with this tablet. So magnesium is +2. Perchlorate, I look it up, it's got that HEE on it. So it's Cl O4, and we'll put it in parentheses right away, the -1 charge. So when I do the swap and drop, I'm going to change colors, make it a little bit more clear. I end up with Mg1, but we don't show ones, ClO4 twice. Then we have iron 2 and acetate. So we got iron with a +2 charge. Acetate's that really long one, so C2H3O2, put the whole thing in parentheses, and it has a -1 charge. So when we do the swap and drop, the top numbers, we end up with FeC2H3O2 twice. Make sure when you're writing these things that you're putting them together. Let me rewrite it over here. So FeC2H3O2. A lot of times when people do this, they just do the swap and drop and they don't really push the letters together, and it looks kind of weird. So sulfate and ammonium. Go back to that. All right, so sulfate, it's got that -2 charge on it. Ammonium is the positive one. It has to go first. So I'm going to write that one first so I don't confuse myself. So it's NH4 with the +1 charge. Sulfate is SO4 with a -2 charge. So I'm going to swap and drop the top numbers, and we'll do it properly. So we end up with 2 NH4s and 1 sulfate. And then the last one, we have carbonate and barium. Carbonate has got a -2 charge. Barium is over in group 2, so it's +2. So that means barium goes first. So we say, all right, we got barium with the +2, carbonate -2. They are already charge balanced. So that means that our final answer would be BaCO3. All right, so now we're going to name some compounds. So the first one, turn my laser pointer on for a moment. We have more than 2 capital letters. So that means that one of these things is a polyatomic ion. Something I should note is a lot of times polyatomic ions have a whole bunch of oxygens in them, so it makes it easier to spot them. So we have potassium and carbonate stuck together in a formula. Potassium is not a transition metal, so the answer would be potassium carbonate. So let me do the next one. All right, so now we have aluminum and oxygen. Aluminum is not a transition metal, and I have them mixed together. It's not just polyatomic ones. There is only 2 capital letters, so I don't have to worry about looking up the list of polyatomic ions. So this one is just going to be aluminum. Europe calls it aluminium oxide. Remember the second one, you have to change the ending to IDE so that people that are listening to it can tell that that is part of a compound. Then we have Fe2O3. So iron is a transition metal, so that means we've got to figure out what the oxidation number is going to be. So oxygen's -2. We have 3 of them. So that's going to be a total of minus 6. That means the iron is going to be, Fe2 is going to be plus 3. Going to be plus 6, but there's 2 of them. I'll write this in 2 places. So that's total, which means the iron is plus 3. The algebraic method for doing this would be 2 times x plus 3 times negative 2 equals 0. So we end up with 2x is equal to 6. So x is plus 3. So the name would be iron, Roman numeral 3, oxide. And then we got SCOH 3 times. I'm going to use the algebraic method. So scandium is a transition metal. So we have X for the scandium. We have 3 hydroxides, and we know this is a polyatomic ion because it is in parentheses. Each hydroxide is minus 1, adds up to 0 because it's a neutral compound. So this is going to be scandium with a plus 3 charge. So we say, all right, well, the name is scandium 3 hydroxide. And then the last one, we got all kinds of capital letters. So we say, all right, well, NH4 is ammonium. And then PO4 is phosphate. Like I said, writing the formulas for things containing polyatomic ions require a few more steps, but naming them is really easy. You just say whatever their name is. It's not one of advance. All right, so we are at the end of that particular lesson. So we looked today at 2 different types of compounds. We have binary ionic compounds, and then we also had ionic compounds containing polyatomic ions. Remember, with the binary, that's where you have 2 capital letters in the formula. So the binary ionic compounds, have to remember, we're always going to put the cation first, followed by the anion. And then the second element, you're going to change the ending of the anion to IDE, so that tells the listener that it has a negative charge. You're going to use Roman numerals to indicate the oxidation number of the transition metals. The exceptions are with silver, because it's always +1. You don't have to worry about it, although it's probably a good practice to put it in anyway. And zinc, which is always +2, cadmium, which is always +2. And then remember that ionic compounds are formula units. It's a ratio of the cation to the anion. They are not molecules. All right, so now we have naming rules or formula writing rules for ionic compounds containing polyatomic ions. So this is where you have more than 2. Didn't leave myself enough space. So polyatomic ions are groups of atoms that are all bonded together covalently, and they act as a single charged unit. It's kind of like a great big lumpy funny looking ion, regular ion. And you got to remember to use parentheses when you have more than one polyatomic ion needed in a formula. I won't do it, but if you want to use parentheses around every single polyatomic ion, that's fine with me. And then polyatomic ions are already special, and so they get to keep their names. So we don't have to change the polyatomic ion ends to IDE or anything like that. And so this last little bit has to do with the picture. Just remember that little imaginary force field around the polyatomic ions, and not to take your polyatomic ions apart. So that's it for this one, and thanks for listening.